Okay, so first of all, thank you very much for having the possibility to talk. Today I will talk about the conjugations. And my talk basically is on some joint work with Krystyna Kamara, Kamila Klisz, and Bartosz Łanucha, and also from together with Artur Planeta and Piotr Dymek. On the end, I will show the papers, which includes the theorems I will put. So let me start with something very, very simple. When we have a complex field of complex numbers, it is the simplest Hilbert space. But except of the Hilbert space structure, we have something more. We have a adjoint, the conjugation. So, what condition it fulfills? It is antilinear isometric involution. So we can think about introduce to make a richer Hilbert space structure to define there some antilinear isometric involution. So when we have any complex Hilbert space, we will say that we have a conjugation on this Hilbert space when it is a antilinear, isometric, and involutive. Why we consider this? I mean, first of all, maybe motivations which come from. I mean, the most important thing is that having the conjugation, we have a richer structure of a Hilbert space. When you have a richer structure of a Hilbert space, we can say more about operators. And first of all, motivation came from physics, in particular from non-Hermitian quantum mechanics and spectral analysis. There is a summary paper by Stefan Garcia, Perdomo, and Mihai Putinar about the physical and mathematical aspects of the conjugations. We will see that historically in what area of physics it can be applied. Also, the motivation comes from complex symmetric operators. I will just explain what is in a minute, but a lot of operators like normal operators, Hankel operators, truncated operators, or Volterra operators are complex symmetry. Another motivation comes from non-Hermitian Hamiltonians. We would like to consider non-Hermitian Hamiltonians, and we have two natural conjugation, as in mathematics say, the time reversal and the parity time reversal conjugation. And we have a lot of authors which from the border of physics and mathematics. First one by Celetti and Graffi and Manoli appears in 1980 about this non-Hermitian Hamiltonians. The next motivation comes from model spaces. We have a natural conjugation in the model space. I will talk about this in a minute. And also we can talk about symmetric matrices. Also, there are some complex symmetric matrices. How this symmetry of operators, why it is important, why when you have a conjugation, we have some symmetric operators. What is symmetric operators? So when we have first observation is following. Whenever we have a conjugation, it is in some sense antilinear self-adjoint. So when we defined the adjoint operator to antilinear operator, here is the definition. So it is antilinear self-adjoint. And the definition of symmetric operator is following. The operator is symmetric when it fulfills, according to this symmetry C, CAC is equal A star. And why it's important equation? Because we can prove a lot about the self-adjoint operators, and they are well known. But in some sense, symmetry is in some sense the self-adjointness. It's just the following are equivalent. When operator is symmetric, it is the same when we take A times C is self-adjoint concerning to antilinear self-adjointness. So we want to say more about the operators which are not self-adjoint, so we can introduce some symmetry, and then we have some more structure, and we have know about operators. This is the general idea why this conjugation is important. Okay, maybe some examples, for some classical examples. Of course, we have a joint where we consider Cn, we have a joint of each component, but we can also take a joint of component and we make the order. And when the operator is a joint, it is symmetric between the main diagonal. When we put this another conjugation, this conjugation which is down, matrix is symmetric according to this symmetry whenever it is symmetric according to the second diagonal. So it is very naturally to consider. The next one is this, what I mentioned, parity and time reversal operators in L2. So when we have a function in L2 of R, the time reversal is just we take a joint, and it is parity time reversal when we take change the order of a time and then make the joint. So it is parity time reversal. And so this is in the space L2 of R, natural conjugation. When we take L2 of a unit circle, the most natural thing is what? It's take to the joint. But when we take the joint, so we change the positive. We take the joint of the operator. Yeah, take the joint of a function. Another thing is when we take the joint Z and F bar, so it means the same when we take the joint of the Fourier coefficients. The next example is just the inner function. The natural, when you have a theta inner function and we have a model space, the natural conjugation, what's on the model spaces, it is just multiplication by this inner function times Z bar times F bar. I will go back to this one. And of course, there's, for example, also the following conjugation, which is down. And it is known that the Volterra operator, for example, is self-adjoint according to this conjugation. Okay. When we start to talk about conjugations, first of all, the first observation we have to notice is that, in fact, we have a lot of conjugations in any Hilbert space. So it is classical theorem when then we have an orthogonal basis. So there is a conjugation in this Hilbert space such that this leaves this orthogonal basis not moved. So we take any orthogonal basis and you can define the conjugation. But so we have a lot of conjugation, but on the other hand, in many spaces, there are some another natural operators, and we can took some conjugation. We have some special behavior. For example, when we have a L2 of R, this time reversal commutes with a shift with a transpose, and with parity time reversal commutes makes the transpose to the other direction. When we consider the multiplication by Z, so this example I show this the conjugation J, just make the changes when we change the order, changes multiplication by Z by multiplication to Z bar. The same with the conjugation which is natural in the model space. But when you take J hash, it just commutes with multiplication by Z. Okay, so we see that we have to choose some special conjugation which behaves very naturally according to the very natural operators which are in the space. Okay, now there are some classical definitions. I will be very quick on that. So it is very standard definition. Okay, and we have multiplication operators, and the set of multiplication operators we denote by script T, script M by T, and you have multiplication by Z, okay, and you have the Teplitz operators. So we multiply by psi and then project on a Hardy space, and the set of Teplitz operators are here. Just use the letter T. Okay, and we have a shift. So this is the classical definitions. Okay, now, so the first thing when we consider, let's consider the space L2 of the unit circle. When we consider the space of L2 of unit circle, so we want to investigate the behavior of this according to the multiplication by Z. So this is the definition of this conjugation J and conjugation J hash, which I introduced in a minute ago. They are natural. We take just the adjoint of the function, and here we take the adjoint to the of each Fourier coefficient. Okay, and what is the behavior of this according to multiplication by Z? This one, when we change, we going to the multiplication by Z bar. So it means that MZ is symmetric with J symmetric. So symmetric according to this conjugation J, and it moves the Hardy space to the conjugate to the Hardy space, this conjugation J, and J hash just commutes with MZ, and it leaves H2 as an invariant subspace. Okay, so this we'll talk about the MZ conjugations. So such conjugations, according to which this MZ is C-symmetric, or MZ commuting conjugation, so that this operator MZ commutes with the operator with this conjugation C. And this is, since we have a natural MZ operator in L2 of T, it means that the most natural is to consider this conjugation. And there are two problems. Find all such a conjugation C, which are MZ conjugations, and find all conjugations C, which are MZ commuting conjugation. And this is the first theorem I would like to say. So in fact, following are equivalent, and most important is the second and the third. So in fact, any MZ conjugation have to be on the form when we have a unimodular function in L infinity, and we multiply J by this unimodular function. So it's just J composed with a multiplication by psi, by unimodular function. Of course, we can change the order here, and it is just technical things. I will not talk about that too much. I will just always put on the right-hand side this J. So we have complete characterizations of how this MZ conjugation looks like. When we look for MZ commuting conjugations, so this is the condition 2. Of course, when we have this commutativity, we have also commutativity for L infinity function. Why this is equivalent? So this MZ commuting conjugation is completely characterized. It has to be of the form of M type psi, M psi multiplication by psi, when psi is unimodular by the symmetric function. So not all unimodular. Symmetric, it means psi of z is equal to psi of z bar. And we take the J hash, multiply by J hash. So it is always the old description. Okay. And as a corollary of this, we can, for example, say that there are not MZ conjugation, so there is no any MZ conjugation which preserve H2, which preserve a Hardy space. And the next corollary is when we have a Z commuting conjugation and it preserves H2, it can be only of the form of lambda times J hash. So it is only J hash according to constant lambda. Okay, now we concentrate on the model spaces. So how behaves the model space in conjugation? So just a brief introduction. So when we have a inner function, when the model space is just the orthogonal complement to the invariant subspace for the shift, so theta H2 of D. And we can define further, it is known that we have a defined, we have a natural conjugation. So we multiply by theta Z bar, and then we take a conjugation on the F, and on the tog on the model spaces, it was showing that it is least invariant the model space. But in fact, this conjugation can be defined on the all L2 space. Okay, and in fact, let me, of course, there are a lot of inner functions, but let me only recall when we take the z to the power n, this conjugation C theta is exactly the conjugation what we have changing the order of the if Cn, changing the order of the coefficients and taking a bar. So which is very natural. And we take also the simplest singular inner function, and the conjugation also multiplication by g lambda. It is a exponential of lambda times z plus 1 over z minus 1. And this is two examples. Of course, there are also many interesting things we call on the Blaschke product and so on and so on. I will not concentrate on that. Okay, and this, as I have taught that this C theta, the conjugation C theta, leave invariant the model space, and it is MZ conjugation. So the natural problem is find all conjugations C which are MZ conjugations, and they leave this model space invariant. And since we have the characterization of all this MZ conjugation, in fact, there is only one, it is exactly C theta conjugation, which leave invariant the model space K theta. So in some sense, the C theta is the unique conjugation to be considered in a model spaces, the one simple model space. Of course, when we consider two model spaces, okay, so we can ask this question also in following way: when we have a MZ conjugation, which put the one model space to the another one, and it can only happen because we have all description of all of this MZ conjugations. It can only happen whenever theta divides alpha. So sorry, alpha divides theta, so theta is divided by alpha, and there is an inner function between alpha and theta, and this conjugation C is exactly C beta, so multiplication by beta and by z bar and taking the adjoint of the function f. So we have completely characterization how this conjugation can look like. Okay, now move to the to J hash. And J hash leave invariant subspace H2, and it commutes with MZ. Okay, and moreover, it moves K theta to K theta theta hash. Definition is according to this hash which is above. So it's not making invariant K theta, but it moves to the some model space which is connected with theta. And we can also put the question whether we have another conjugation. And also, the answer is following. Maybe the little bit even general. So when we have a conjugation with move K alpha to K theta, and it is MZ commuting conjugation, it can only happen when theta hash divides by alpha, so is divisible by alpha, so alpha divides theta hash, and then conjugation is the only one, so it is J hash, according to the, of course, constant. Okay, when we take alpha equals theta, this is exactly the one conjugation J hash. Okay, now on today's talk of Stefan was about Teplitz kernels, because we know that when we have an inner function, in fact, the model space is the kernel of the theta bar, of the bar of this inner function. So a lot of things which are true for model spaces are also true for a kernel of Teplitz operators. And of course, not all Teplitz operators are, kernel of Teplitz operator are not, some of them are just equals 0. There is a lot of papers by Hayashi, Haidt, Sarason, Poltoratsky, Makarov, and Kamara and Partington, which characterizes all this when these kernels are not 0. On Ramon's talk was some consideration about that, and then so we will consider the kernel of Teplitz operators, and in fact for any unimodular function we can define the two conjugations. We multiply this by this modular function and compose with J, and we multiply and compose with J bar. And of course, according to this notion, this C theta is just multiplication by so theta Z bar, and then taking the J. So when we have a kernel, in fact, kernel is invariant. What was also on the Ramon's talk, on the Stefan Garcia talk, is invariant for this conjugation. But moreover, we can ask the same question as for model spaces for kernels of Teplitz operators. Whenever we have a MZ conjugation, such that the kernel is not empty, and this C conjugation, this conjugation C leaves invariant this kernel, when it can happen, and it can happen only when this conjugation C is of this form. So we multiply by phi Z bar and take the J. So it is the only conjugation with which leaf invariant this kernel. And moreover, when we consider, we can extend this relation between an inner function to the all unimodular functions. So G is smaller than H when H over G is in L infinity. H infinity, sorry. And we can ask a little bit more. So when we have a MZ conjugation, and we have that, and we have a eta, we have a unidar function, eta 1, multiplied by the kernel of some function G. And this conjugation C moves this to eta 2 times kernel of H. So it is, of course, in a special case, it was before in the scholarly when eta is equal 1 and so on, and eta 2. So when it can happen, we have with Christina in the previous paper also this for model spaces. Here is also true for kernels, and it can only happens that G is bigger than H, and moreover, only such conjugation as of the form C psi T, where psi is something between eta 1, eta 2, G bar, Z bar, and eta 1, eta 2, H bar, Z bar. So we have full description of a behavior. And it also corresponds to what Christina talked about, the decomposition of the kernels, because according to this conjugation, we can also consider the let's make some decompositions. This kernels make some decomposition according to these conjugations. Okay. Now the same thing for commuting conjugations. Okay. For NZ commuting conjugations, when we have a same inclusion, yeah, it's only possible when H hash is smaller than G, and the only conjugation as of the form with C hash alpha T, when alpha is between these two unimodular functions. So we have a full description. I mean, of course, we have make a corollary of that. So now the other direction, when we have a kernel of C of kernel of TG includes in kernel of TH, then how this conjugation can look like. And we have also full description. Okay. Now we talk about the spaces on a unit circle, L2 on a unit circle. Now how we can move it to the real line. And just we have a conformal map. I'm just very quickly because it is known, and we can consider the hard space on the upper half plane, which is a subspace of the L2 of the real line, and we have a L2 U2, the unitary operator between L2 of unit circle to L2 of real line, which lives invariant hard space. Here is a formula. And we can also define the formula for the operators. So U2 wave, it just moves the operator on L2 of multiplication operator on L2 of the unit circle to multiplication operator on L2 of R. And it is just from the both sides U2. But of course, we can also define the U infinity from H infinity of T to H infinity of R, which is just a composition with this holomorphic conformal map gamma, and okay, and of course we have also the multiplication operator. Multiplication operator by natural definition. So I will just go very quickly, and the Teplitz operators, and then we have a we have a map, symbol map on the L infinity to the multiplication, L infinity multiplication, also for the Teplitz. And in fact, we have a full, this diagrams commutes, so it means that there is a full agreement between the multiplication operator on a unit on the circle, on the space of the circle with multiplication of the real line. And the same with the Teplitz operators. Okay, and now the conjugations of L2R. The conjugation of L2R is just the natural, we take the joint, or I put in all the conjugation which are on R with the symbol R here to be clear where we are. And the R hash is just we change the direction with minus T, and so this is this check here and make a bar. So exactly JR, it is time reversal, which is used in physics, and this parity time reversal of another one. Okay, but we can of course go a little bit more further. So when we take the unimodular function, I haven't written this here, but it's obvious. Capital Psi unimodular, we can define the C psi r as a multiplication by psi and then taking the bar, and also C hash psi r as a multiplication by psi and then taking the j hash, so check and bar. Okay, and then when psi is and also we can use this unitary between this L2 spaces, and it's exactly nice commutes with also with this conjugation C psi r. So when this unimodular function psi small is a unimodular function, then we can obtain the conjugation C psi composed with gamma r by this formula, and then we obtain the commutativity of these diagrams. Here is, of course, the sign minus appear, but it's according to calculation. But of course, for this hash, we need to have a psi symmetric. Okay, and also this conjugation J and J hash, nice properly according to U. And so we have the nicest is the last one, when we have a minus J hash and J hash R, because here, of course, J goes to not to conjugation with a symbol gamma here, with a symbol gamma. Not okay. So gamma, so this is multiplication by 1 goes to the multiplication by gamma. And here, multiplication by 1 here on this side goes to multiplication by C bar. Okay. Okay. And now, so just a notation of G lambda is just a composition with this G lambda with gamma. So it gives e to the I lambda t, and using this commutativity of diagrams in some sense, we can move a theorem which was on a unit circle to the real line and upper half plane. So when we have a conjugation, CR, then following are equivalent. The most important is first one and the fourth one. So in the first one, we have a we know that according to this conjugation CR, we have any conjugation CR on L2 of R. The conjugation CR makes multiplication by G lambda, mg lambda becomes symmetric according to this conjugation. And this is exactly can happen. Of course, this is equivalent 1 and 2. So it's enough to show that this is according to gamma of a one function. Then it is in fact for all functions. And in fact, it can only happen whenever we have a unimodular function and the CR is just multiplication by capital Psi times JR. And the similar is for when we have a commutativity between, so we have a conjugation CR and we have a commutativity with mg lambda, then it have to be of the form m's multiplication by psi, capital Psi, j hash r, but it's only for even unimodular function, So the symmetric functions go to the even functions. Okay, and now we can also talk about the kernels. We can also talk about the kernels. So when we have any conjugation which makes the M multiplication by G lambda symmetric, and it makes invariant the kernel in this sense that we have a multiplication by some gamma unimodular function. It is important that we have in this formula. On the last example, I will show how it works. Then makes invariant, then it can only happen when we have unimodular function b, and function b between this gamma 1, gamma 2 bar h and gamma 1, gamma 2 bar g, and this is just the multiplication by b times jr. The definition of the for a unimodular function of the on the real line is the same. What does mean equality? Okay, and this is just the corollary when I take h and g. So gamma is, and this is exactly for a kernel. So I move the theorems for the kernels of the for kernels of the Toeplitz operator on the unit circle to the kernels of operators on the real line. So it's also work, of course, for a model spaces on the real line as a special case of kernels. So it's only happen, this inclusion can only happen whenever b is between h and g, and this conjugation is multiplication by b jr. Of course, in a case when g is equal h, we have only one conjugation, which can happen according to, of course, multiplication by constant. Okay, and maybe example. So when I take CR, of course, which make this G lambda symmetric, and I take the model space connected with the function G lambda, with the exponential function G lambda, exponential of I lambda t. So I move this model space connected with small g lambda on a unit circle to the real line. Yeah. So, and I have this inclusion. So I have some g gamma, some unimodular functions like this kernel. This moves this symmetry. Sorry, this conjugation moves to g gamma 2 to another model space. It can only fulfill when this numbers lambdas. This is inequality between numbers lambda 1 and lambda 2, and there is a b between lambda 1 and lambda 2, and the only conjugations can be conjugation connected with this inner function g when the number here is b plus gamma 1 plus gamma 2. So it is completely characterized. Okay. And of course, when we have a simple case, when we with g is, sorry, I have no time, I go further. Okay. Now, what can happen when we move L2 by Fourier transform? So there are definitions of Fourier transform and definition of convolution. I will not, a transformation and definition of check. I will not go on this. Okay. And then, now when we use the Fourier transform, it makes funny that this diagram is commutative both ways. So starting with J hash, and then Fourier transform, it's the same going Fourier transform to J, and also by the other direction. So this is the intertwining property with Fourier transform. Okay. Now there are some definition concerning the distributions. maybe I will not concentrate on that. But when I have a distribution mu, I can define something which turns out to be a conjugation, C hat mu convolution with F bar. And similarly, mu hash connected on F, it is just the mu convolution with F check bar. So in fact, it is mu convolution with JR or mu convolution with J hash. I can simply connect like that. And of course, we can consider the delta Dirac. And when we look for delta Dirac and explain this, so in fact, when we have a delta Dirac in a zero, it takes G. It is a convolution J or J hash, and C hat hash is the convolution connected with the symbol delta Dirac in the point A. But in the case when we have without hash, it's not a conjugation. So we have only conjugation with a hash. Okay, and the question is when the C hat mu becoming a conjugation. And in fact, this becoming, it can be extended to conjugation of RR if and only if it is a tempered distribution and F Fourier transform of this distribution mu is unimodular even function. And moreover, we have the following commutativity. And with the hash, it can be extended to the conjugation even only if it is a tempered distribution that Fourier transform is any modular function. And we have also then the following intertwining with the Fourier transform. So this intertwining shows these diagrams. So in fact, it is easier. Here we have a Fourier transform of a check of the distribution. So it is easier not start with a distribution, but it's easier to start with any unimodular function of R, and then take the distribution as a value of a Fourier transform of this unimodular function, and then we obtain this conjugation. So this is the way how to produce conjugation on a L2 real line using convolution. Yeah. Okay. So this is a Fourier transform of this unimodular function convoluted with J or convoluted with J hash. And now we can have a lot of conjugations. We take the unimodular function signum, for example, and we have a convolution. Yeah. So the Fourier transform is p-value, and this convolution is nothing else like minus I Hilbert transform of X check hash. When we take the just the characteristic function of the interval minus I, then we obtain the following conjugation. So it is sinc function convoluted with F check hash minus value of 0. And we have only one because it is the signal is not symmetric. This is symmetric function, so we can apply to the both. Okay, and there is another example. We can have. Okay, and now we can try to have how behaves this this conjugation C hat hash mu, C hat hat according to the transformation. And in fact, when we have a hash it changes the transformation tau x to minus tau x. And when we have without hashes, it's just commuting with transformations. So it is just as we have with J hash and J. Yeah. Okay. And moreover, I mean, now we can ask when I have any conjugation C hash and it behaves properly according to the transformation, then it's only possible when there exists unimodular function, and this conjugation is just defined by the convolution with this Fourier transform of unimodular function with J hash. When it commutes with transformation, it just only can happen when we have even unimodular function, and we take the Fourier transform and convolution with JR. So we define, in fact, all this time reversal conjugation. How can JK be described? Okay, and just on the end, to show the application of that, we have a convolution, we have a conjugation, which is makes changes with transformation for the converse transformation, and it leaves invariant the L2 space of the interval A1 to B1, A2 to B2. Can we describe all such this conjugation? And we can. We can, using, because we know that so in fact, we can, using the model space, we can know that we can move the space L2 of A1, B1, we can explain as some example of the model space moved by some function. And in fact, it can only happen, so we can have a conjugation of this type, even only if the interval, this one is a bigger interval than this one. And moreover, each conjugation is just the convolution of the Dirac delta of any gamma between these two numbers with J hash. So in particular, when it's the same L2 space of the same interval, same length of the distance valve, there's only one conjugation which is explained here. Here are papers which are, some of the work is in progress, some are published, and here are the references, and much more of them also, but I'm not presenting them. Thank you very much, and I'm sorry for being a little bit late.
Thank you very much. You weren't late at all. Now we have time for questions. Yes, and someone is asking if you could please share the slides.
As just Ramon said about the conjugation of the kernel, and this is exactly the answer for his remark that this is the only one what he mentioned.
Mm-hmm. Right. But I'm going to share the slides. Is it fine with you, or?
Yes, you can share this. Yeah. Maybe I sent. I sent to you. Yeah.
Sure.
What's that? How? You want me to not to share? Yeah.
No, you can put it on chat, Marek. Marek, you can share it on chat.
Okay.
It's possible there is a file button, so you can just click it, I guess.
Okay, I will do it in a moment.
Thank you.
And in the meantime, if you have any questions, you can write them in chat or just ask them.
I just will share on the chat, but I have to find the correct. So I think it went.
Yeah. Done. So if there aren't any questions, I guess it's lunchtime. So if there aren't any questions, then let's thank the speaker again. Thank you. And we'll see you tomorrow for a colloquium.